Now, good afternoon, everybody. I was told that I should stand here, although I don't like it because I usually like to move as a teacher, and I used to be a teacher, and I liked it, and I was enthusiastic about it, and I had a lot of passion to my profession. I identified with it. All the good words which were said, I felt them. But for the recording, I should sit here and try to do my best. So my talk will be about how does research in science education, what does it say about student learning? And if we continue, this is our Department of Science Teaching at the Weizmann Institute, which is a research institute in chemistry, biology, mathematics, many scientific disciplines, and also interdisciplinary ones. And we are dealing with teaching and having the advantage of having our scientists with us. I have my private one, and it's always, we are very thankful to get their input and vice versa. So here, I'm going backwards, I see. Okay, so we can see that science education, we have all these buzzwords, but they are really used by us. We deal with in-service education. We deal with innovation in science, and we interpret it to science education. We have very good tools, also technical ones and scientific ones. Ron mentioned the AFM, Atomic Force Microscope. We have it in our department because we try always to take the innovations in science and try to deliver them, to transfer them to teachers, to students, to our curriculum, and so on. And of course, students, strategies, PK, PCK, motivation, you name it. Everything that you heard before, and I'm thankful to the both presenter, Parker and Jan Lundell, for giving all the basis and the good standards for what I'm going to talk. Okay, when we are talking about learning, what do we mean by learning? What do you think about it? And here we have, sorry, I need a little bit to move because I need to see where it is. And if we look, we can see one of the French in 1992, late French. Unfortunately, he passed away a few months ago. And he's talking about the most, as we can see, psychological influence on curriculum thinking in science since 1980 has been the constructivist view of learning. Larry, that's what you said before. And the students need to learn to cope with their life in society. We are not creating scientists. We are not developing only scientists. But we need the students to be individuals in society and understand what's going on and participate actively in societal discourse concerning social-scientific issues. I had some references here about the work, but I want to mention that Mia and Jack were two scientists, science educators, I recall, the 25 years ago were the whole time searching this field, and this is also my opportunity to say thank you for inviting me to give this lecture. Now, if we continue, what are the components of learning, of teaching? So we can see the teachers, we can see the students and the curriculum. And of course, the students are our aim. But just, being maybe a little bit superficial because there are a lot of components, a lot of factors. But I prefer to concentrate on something. It's a huge issue. So if we look that when we are talking about the curriculum. We want to emphasize the relevance, the inquiry-based, the contemporary, context-based, driving questions, need to know, and so on. When we are talking about students, we look at the cognitive and affective skills, motivation, interest, learning difficulties, misconceptions, and teachers who really are the key to any innovation. Then we talk about the pre-service, in-service, cultural effects, PCK, which we heard about it from Jan Lunde, from Jan, and the professional development, of course. And all this, how do we measure it? How do we know that what does research say to us? We need to measure. So we have different measures. For example, questionnaires, interviews, student reflections, teacher reflections, class videotaping, observations, and of course more and more. It's just, everything is only examples. Now, the standards in science education, and we heard about standards, there are the whole time. They deal with the current, the content of science that every student should learn. Somebody mentioned before, I think it was Jack, when we studied, for example, chirality was part of our curriculum. I'm not sure if now it is, which doesn't matter in order to raise curiosity, but it changes with time. The pedagogy of teaching science, the assessment of students, professional development of teachers, and organization of learning. Very, very main ones. Then, all that all this pyramid goes up to the student, because we have even more influences. We have the family, we have the environment, we have the parents, we have the colleagues, the student colleagues who also influence the students. Everything influences learning, and we have role models, which we should think about it very, very thoroughly. A role model can be a very good influencer on student learning. Students, I will now focus on it. What do you mean? Cognitive and affective skills, motivation learning versus learning difficulties, misconceptions and alternative conceptions, which is actually the same, but you know, some people don't like to call it misconception, but alternative conceptions, assessment methods, language, learning environment and cultural background, which is very, very important in learning, the culture of the environment. Then, if we look at what was mentioned before, cognitive and affective components. So Wahlberg, in 1975, he talked about aptitudes, instruction, environment, and ability, development, motivation, instruction, the amount versus the quality, and how should we match it to each student. There are students that too much is too much. Environment, home, classroom, peers, television, now the communication, or now the media have a huge influence on learning. And if we look, all that brings to learning effective, behavioral, cognitive. I'm doing it quickly because I want to bring many things, not very deeply, but to give a larger picture. The motivational pattern, it was Leah Dar in 1964. It was a Israeli educator. She identified the achiever, the curious about students, the conscientious, and the social. How students learn. For example, if we look at the curious students is the one which is very much preferred by many, and Ron in his talk mentioned it a lot. But we have also the conscientious, who doesn't want to look bad in front of his colleagues or teacher, the social who studies with other students, and the achiever, that it's not bad, none of them. But maybe we can have all these 4 types of students in one student. Maybe we should strive for it. So we have here also references to some papers or some research studies about this, because all what is said is said in these papers. Then, if we look, how do we match our strategies to the students? So, look, drinking, yes, if we look how they drink, if we don't give them the right vessels or the right glasses, so we are losing them. We should think about the pattern for the students according to what they are, and not according to what we think they are. Then the language. The language has a few parts. I'll start with the second one, not with the first one, the science language. Again, Ron mentioned it, but it can be very embarrassing. It can be very difficult. I bring an example from chemistry, because my discipline training is chemistry. But for example, if we say H2O, so it can be, it's a joke, but it's not so far from reality. We start with H and we go until O, H-I-J-K-M-L and O, it's H2O, isn't it? So this is about other things that students think also. Or we have the formaldehyde. Biologists and chemists know about it, and which the formula is HCHO, or it can be written as CH2O, and which is like seawater, if we look at it, the language. And when we talk about like chirality, for example, if we have the concepts, we need to explain what it is. What it is to the students, exactly. We need to say the same atoms in the same molecule. It's even the same, something with a structure, but there are 50%, for example, in a synthesis are like that, and the others have an influence on the light, another influence, and so on. So there are many examples for it, or percent. In Hebrew, percent, for example, the word doesn't mean anything to students. And it causes a lot of troubles afterwards in combining the mathematics with science. Then we're talking about the language in cultures. Now with the immigrants in the last 20 years in Europe and everywhere, so the language became a huge challenge, because students need to study in a class, for example in Germany, and they don't know one word in German. And even if they studied, again, they have to be acquainted with the scientific language. So Professor Sylvia Markic, for example, she does a lot of work with language, because she herself was an immigrant from Croatia to Germany. Now, if we look, this was about students, but again, we can talk about it much more. It's just to show how problematic it is. The curriculum, is it relevant to students' life? Is it updated according to scientific and technological discoveries? Is it updated according to societal and economical changes? Does it enhance scientific and technological literacy, understanding what's going on? And again, we go to the COVID-19. Does it increase students' interest and motivation to study science? Or does it enhance students' interest in scientific careers? And there is a nice project that Mia, Jack, and the team are leading at the University of Tartu, and we are honored to be part of it. It's the addressing attractiveness of science career awareness. So does it do it? Does it hint to it even? Or just talking about formulas and equations, or in biology, the number of bones in a chicken. So how? What kind of curriculum or curricula can we recommend? We can recommend the inquiry type approach, which has a lot of asking questions, hypothesizing, drawing conclusion, argumentation. It was already recommended by Aristotle, Socrates, and all these people, the Socratic dialogue. Design-based, the group of Joe Krejcik, David Fortis, and I also was honored to take part in it. We developed a design-based curriculum. It has something with engineering, with a need to know, with driving question, social scientific issues-based, using a contemporary research-based versus a historical approach, or both. How do we combine it? Or maybe a teacher should, a curriculum should deal with all these components. Let's see what is best for the stakeholders, what is best for the teachers in a certain culture, and so on. But there are the possibilities. Then, if we try to explain what is inquiry-based and argumentation, an example. Here, students conducting the inquiry-based type experiments. We have it in physics in our department, biology, we have it in chemistry. So we can see explanation of observations, constructing a hypothesis, defining research question. It's not the real order. Drawing conclusions, working in small groups. We have all this together, and here is a long reference to our work, which was published lately in a book that will be soon published, and in the Israel Journal of Chemistry. Argumentation. What do students learn about it? They learn about what is a claim and what is based on. It's based on data, on an artifact, on evidence, and then both together we need to give an hypothesizing, a scientific explanation, and this all goes to an argument. Of course, it's very simplistic here, and it's more sophisticated, but it's based on Toulmin's model in 1958. Then, what does it do more? It focuses on discourse. Dvora Katsevich, her PhD was based on it, and she had really good results about what argumentation, how does it help in enhancing students' curiosity, students' ability to ask questions, to hypothesize, and to be open to new ideas. Then we have context-based, design-based, social-scientific issue-based, and using a contemporary research-based for this. How do we see it? Context-based. For example, it was design-based. One of the projects or the modules which we developed with the group of Joe Krejcik was, how can I design a cellular phone that is safer to use? It's a driving question or a need to know. It's context-based, it's design-based. It's, I'm referring to what was said before. Is it a problem? Is it a scientific question? Or it's both? And we can see that we deal here with radiation, plastic, sound, disposal of batteries. And here are the references that were mentioned by Yari in his talk in 2004, and then in 2005 about also real problems in science education. And the last one, and of course, I just forgot to say it, it's a contemporary question, because cellular phones are something that is very contemporary. And the last one, a historical approach, which has the less success in science education, I'm sorry to say. We tried a lot to push it, but with no success. And we think that it should have a huge impact on science education, and research is showing it. To know what something is today, we have to learn about what it was like yesterday. It was in a Chinese daily newspaper in 2002. And we can see here also Lavoisier, who was one of the first scientists, we can call it scientists, who changed the theory of Aristo, with the world is composed of 4 elements, and by somehow not discovering that the air has a lot of airs in it, oxygen and so on, he changed a lot in this theory. So we don't go over the list, but we can see how long is the list, and it's only a short list of research in science education that deals with incorporating the history of science in the science curriculum. Research findings from the researchers show that initial student scientific knowledge is very much similar to the knowledge of scientists in the ancient work. They also think that the atoms are small balls and so on, and is made of observation conclusions that are often intuitive. Children believe in what they sense and tend not to believe in what is out of the scope of their senses. And by using the historical approach, we can change it. Now also, it causes a better understanding of the nature of science. And again, the nature of science, or how scientists work, like Ron talked before. How is science generating evidence? How does science contribute to the development of scientific skills? How do scientists develop their scientific knowledge? Even if you don't really understand the phenomenon, if we don't really understand the formula, if we don't really understand what the scientists explained us, if we're interested in it, if we want to know how it is, we will go afterwards, we will look in books, we will ask people and understand. It's very easy for me to use this example. If I don't know exactly what chirality is, but I can see that chirality is influencing these characteristics of the compound, agriculture, our body, sugar, bacteria, and so on. So I see that there is something here that is worthwhile learning, and I will go and try to learn. And here the scientists showed me a graph. I didn't understand the graph. Maybe I should learn how to read graphs, how to read tables. Maybe I should try to know what temperature does to compounds. So these are the need to know, the driving questions. And if we look on history, how scientists develop their scientific knowledge, and we look at Galileo, everybody thought that it's a fantasy, so it can be a role model for people, something to look at, students. One of the persons who dealt with it a lot, and he passed away a few months ago, was Norman Lederman, Professor Norman Lederman, and this chapter 28 in Sandra Abel and Norman Lederman handbook is about the nature of science, past, present, and future, and a lot about history and philosophy of science. So the recommendations about it are that historical approach may help to achieve a better understanding of the essence of scientific phenomena, methodology, and overall scientific thinking. And this integrates scientific development and historical analysis may help to achieve a better understanding of the nature of science and understand that we need to learn the whole time more and, as was mentioned, to do more research and more think about it. And the students should become familiar with various projects of scientists and the effect of various cultures on the scientific development, because it's culture that also can hinder or can encourage the development. Sibella Duran, for example, from Cambridge University, Oxford University in England, she deals a lot with it, and we had together research about it. So, teachers, and here I'm going to do it very quickly, because Yari did it before and very extended, but just I can't finish, the whole circle without the teachers, that they are the crucial ingredient and meaningful learning in inquiry activities and clarify understanding, misunderstanding with peers, and so on. They should get a sustained preparation and support in guiding their students and an ongoing, continuous professional development. And the critical role is of teachers in attending this goal of quality education in science is highlighted in the research literature on education. And of course, we have here a quotation of Osborne and Dillon in 2008 about Europe needs more scientists and about the role of education role of teachers in recruiting more people to science. But there is a lack of effective communication between students and teachers. I was a teacher, as I told you, and I know that sometimes I missed it as well, and it can cause a mismatch between what is taught and what is learned. And when I hear meaningful learning, sometimes I wonder, when somebody learns something, it means that it was meaningful, even if learned it in a wrong way. So learning is not always what I would like that somebody will learn, but if he learned it, even if it's wrong. And then in the context of science teachers, there is no symmetry between the nature of teachers' understanding of particular science topics and students' ideas. And therefore, the challenges for teachers are really, again, Yari, I apologize, but I give also another perspective. Acquaintance with the curriculum, designing lesson plans, assessing students' achievements, especially alternative assessment, which is a whole story. Teachers know what I'm talking about it. Managing classroom, ability to conduct changes in pedagogy, in new curricula. Developing ownership of innovations in education, becoming more student-centered. The ownership is very important. Having self-efficacy to what you are doing, preparing the future citizen in a very mixed cultural society to enable, again, students to be reflective, creative, to identify with what they are doing, and to feel that they can to raise their self-efficacy. And again, the standards of professional development were already mentioned before. There is a book which I recommend about professional development. Here we have all the words which were mentioned before. I missed the identity because we dealt it a lot with communities of teachers. Models of professional development. All these models were tried out in our department, and you can see it according to the names. The names are of people from our department, students and faculty people, developing of leadership, involving teachers in developing of assessment, development of materials and assessment of the science curriculum, evidence-based professional development, having artifacts, bringing them and transforming them to evidence, actual research, which is my favorite. Teachers are researching their own work, and communities of practice, which this is for another lecture. It's a project of, in the last 5 years in our department, very successful and very much encouraging teachers to continue and learn and do things. So, all the research together, which mentioned before, what you know, it can also bring groups together. Based on research, there are projects. Based on research, there are exchanges of scientists who continue to research. One of them, the project was profiles, again, with the University of Tartu, Mia and Jack, with 22 countries, and it dealt with everything which was mentioned before. If you can look, inquiry, design, problems, argumentation, relevance, and so on. It was context-based, relevant, focused on IBSE, socioeconomic problem solving, decision-making, scientific literacy for all. As if it combined a huge research of many decades into one project. And, of course, focused both on intrinsic, extrinsic motivation of students in the learning of science. So research also brings together scientists who want to continue to work together, to have new innovation, to do things and to raise more questions, more research questions in order to move the scientific knowledge on. And again, we can see the self-efficacy and ownership of teachers increased according to reflections of teachers, students' attitudes also increased, and we can see that school science teaching became more meaningful. So, another project, Mia will tell you about it in many other, let's say, symposia. It's about the science career. It's also as a consequence of all the research we did together. So what have we learned? We have learned that we need to take everything which we mention, all the research together, into our consideration when we develop a new curriculum, implement it, do the professional development of teachers, and we're thinking about students, abilities, motivation, interests, and so on, and culture. You can see all of this again, learn and lead, and innovation, motivation, and thank you.
And thank you, Rachel.